Dr. Retzer, I've actually known since I was 23, so that's been about, what, 10 years ago?
Almost.
Yeah, so almost 10 years. And so Dr. Retzer is actually one of the best data scientists that I have come to know. And so he's worked 25 years in the market research industry for some major corporations. One of the things that's kind of unique about Dr. Retzer is that he always bridges basically what he's learned in academia to how to apply it in industry. And so he's very active with regards to conferences. He's won several Best Presentation Awards at the AMA Art Forum, the Advanced Research Techniques, and also Sawtooth Software, which is a little bit more on conjoint, discrete choice, etc. Right now, he is a professor at the University of Wisconsin-Milwaukee, and he is also a chief research officer at ACT Research. And again, you know, he's really kind of a renaissance guy. He knows a lot about a lot of different topics. And so he especially knows a lot with regards to data science. So we give a warm welcome to Dr. Retzer, and he can start. Thanks.
Wow. Thanks, Dr. Fugger. I hope I can live up to those kind words. Hello, everyone. It's great to be here, and it's an honor to be asked to do a keynote presentation. I'm going to be talking, of course, about building a recommender system using R. So I actually do have some R code in here that I can show you guys. Before I get started, though, I wanted to talk a little bit about an experience that I had a few months back that perhaps some of you guys can relate to. I was traveling to a conference out of state, and I had to fly out of Milwaukee's Mitchell Field. And I was walking down the concourse, and I stopped at one of my all-time favorite stores. It's called In Motion, if you guys are familiar with it. It's sort of an electronic gadget and accessory store. It's got really, really cool stuff. That's one thing that characterizes it. And the other thing that characterizes it is that it's incredibly expensive. Right? So I was going into that thing to get ideas about what I might like to have, but I never buy anything. So I went in there, I stopped in the store, and I saw this. It was an organizer for headphone cables. And I'm kind of a nut about keeping cables organized and neat. You know, I don't like a rat's nest of cables, regardless of what they are. And so I thought, hey, this looks kind of cool. It was actually made out of leather, and it had a snap on it. I got some cheapo plastic ones, and I thought, this one looks, you know, kind of classy. I thought maybe I'll check it out. And so I was looking at it. It was kind of interesting, and I flipped it over to look at the price. And for this 2.5 to 3 inch piece of leather with a snap, the price was $24. And I thought, wow, they used to be expensive, now they're incredibly expensive. And so I put it back down. I remembered the name, the brand name of the product, and of course I could describe it. So I went on my trip, and when I came back, I went to my computer, I logged into my Amazon account, and I did a search for this thing. I typed in cable organizer, headphones, that sort of thing, and I found it, the exact same thing, the exact same product, from the exact same manufacturer. And unfortunately on Amazon, it was also selling for $24. So I thought, okay, you know, I don't need this thing that bad, forget it, I'm not going to buy it. And I did a couple of other things, and it couldn't have been more than 10 minutes later, I thought, I'm going to jump over to, I've got a digital subscription for the Wall Street Journal. I'm going to jump over to that and just, you know, take a look at the headlines for the day. And so I did that, and I opened up the Wall Street Journal homepage, and all of a sudden on the right-hand side popped up an ad for cable organizers. And it wasn't a cable organizer for headphones, but for like USB cables and things you would connect an external hard drive or microphone or speakers. I got a bunch of those, and I thought, that's really interesting, because I could use something like this. And I thought, wow, what a coincidence that I just got done searching for this, and here I got this recommended. I thought that only for a second, and then I realized, oh, wait a minute, Amazon's recommender system noted what I looked for. It came up with a recommendation, and actually passed it along to another website, which I thought was a little creepy. I didn't really like that too much, but I realized what it was doing. So it's sort of like, you know, people who bought this also bought this, and people who looked at this also were interested in this. And yeah, so that's my story. Now, that's a recommender system. There's a lot of other recommender systems that are out there that, whether you are aware of it or not, you probably are familiar with. Things like Facebook, Twitter, or LinkedIn. These sites all recommend other people that you should somehow connect with. They might have the same personal interests that you do, like on Facebook. They might have the same professional interests that you do, like in LinkedIn. Or they might have the same political ideology or something like that on Twitter. And if you follow one, they'll come up and say, oh yeah, this person also thinks somewhat similar. You should take a look at their Twitter feed as well. Amazon I mentioned before, but Amazon also, in the app, if you search for something, it'll, at the bottom of the search, it will say, here are some other items that are similar to what you're looking for. And I actually find that to be really handy, because a lot of times there are features and attributes for products that I wasn't even aware I needed until I saw it in Amazon, and then I go ahead and buy one of those things. So that's actually pretty cool. Last FM, Spotify, Pandora. I subscribe to Pandora. It's a great music service. They will look at characteristics of music that you say you like, and it will suggest other songs to add to your music library, which is pretty cool too. And of course, Netflix will suggest movies that you might like based on movies that you've watched in the past. So I kind of gave the impression that the recommender system that I saw the first time with Amazon was a little creepy, but they actually are pretty valuable. They do work very well, especially for suppliers, people selling things, for a couple of reasons. They help you find products you may want to buy faster. Right? So sometimes there are things that you're just not aware of, and it would take a lot of searching or digging to find those things. But if you search for something even tangentially related, you might discover them pretty easily. They also promote cross-selling. Right? When I was in industry, if I had a nickel for every time I heard a salesperson say cross-sell, upsell, cross-sell, upsell, I had a big pile of nickels, but they said it a lot, and cross-selling, suggests additional products. So I remember searching for a travel mouse, a small mouse that I could put in my backpack and then use when I was at a conference or something like that. And on bottom it said, hey, by the way, people also bought this nice little case, carrying case, so it doesn't get scratched up in your bag. And I might as well get that too. So it does that. Also improving customer loyalty by creating a value-add relationship. That I definitely believe is true as well. A lot of times, if I'm looking for a particular product, I might just go to Amazon rather than directly to the manufacturer, because Amazon makes all these other recommendations, and if I go to the manufacturer, they're not going to do that, right? They're going to say, hey, you came to the right place, this is what you want to buy, whereas Amazon will say, hey, here's some other alternatives. You may like them a little better. So what I'm going to do today, I'm going to talk about specifically one particular type of recommender system, but before I do that, I want to give kind of an overview of the different types of recommender systems that are out there, right? And then just focus in on one. Obviously, don't have enough time to talk about all of them. But recommender systems can be broken down or categorized in a couple of different ways. Probably the first way is to differentiate between content-based versus collaborative filtering. So for example, content-based looks at the actual features of the product or the item. Right? What differentiates this thing? And if you like it, find other things that have those specific features. A great example, and I've got a reference to an article at the end of this, is Pandora. Right? So if I go to Pandora and I say, I really like this Creedence Clearwater Revival song called Run Through the Jungle, it's going to take that song and it's going to say, okay, let's think about the rhythm, the feel, the influences, the instruments, the artists, all this sort of thing, and it's going to make some recommendations for me. I see some younger faces in here, and people are sitting there thinking, what band in the right mind would call themselves Creedence Clearwater Revival and Run Through the Jungle? Right? This guy's making this stuff up as he goes along. Trust me, there really is a group like that, there was, and they really did have some good music, at least I thought they did. Okay, so that's one way that we can create a recommender system. Another way, another general sort of class, and this can be broken down a little bit as well, is something called collaborative filtering. And collaborative filtering involves, in a sense, collaboration with many other purchasers or users in terms of getting their ratings on products or movies or restaurants or whatever it is, and then using that to help make recommendations for the individual. There's a couple of ways we can employ collaborative filtering. One is through something called item-based collaborative filtering. Item-based collaborative filtering basically says that people like things that are similar to other things that they like, or they will like things similar to other things that they like. So I'll use movies as an example. We'll talk a lot about movies today. Imagine for a moment that there are two movies out there, movie A and movie B, and I can see that they are very similar to one another in terms of the ratings, right? So I go back and I've got a database with maybe a few thousand respondents, and I look at items A, or movie A and movie B, and I see that the same people, or different people, rated these two movies the same, okay, throughout my entire data set. So if somebody really liked A, they really liked B, and if somebody didn't like A, they didn't like B, right? And I get a measure of similarity based on the ratings, okay, not the features, but based on the ratings between these two movies that say, hey, you know what, A and B are quite similar. Now, it turns out that I watched movie A, but I didn't watch movie B. So, am I going to like movie B? Well, if I like movie A, then I'm probably going to like movie B. And if I didn't like movie A, I'm probably not going to like movie B. Okay, so that's item-based collaborative filtering. Okay, starting off by looking at the similarity between the items. Another way, the way I'm going to talk about more today, is something called user-based collaborative filtering. In user-based collaborative filtering, I'm going to predict or encode my preference for a particular product by looking at the preferences of people that are like me, right? Like me. Let me introduce some terminology. I'm going to call myself the active user. The active user is the person you're trying to figure out the predictive rating for that person. And as the active user, I'm trying to figure out whether I would like a particular movie or not. In order to do that, I'm going to first find out who are the people in this data set that are similar to me. And again, I'm going to do this by looking at rating patterns. So who rated other movies in a similar way that I did? All right, so maybe John, Paul, and George, these three folks, rated movies in the same way that I did. I'm going to consider those three guys to be in my neighborhood, in a sense, right? They're close to me because they're very similar. And if there's a movie that I haven't seen, but those guys have seen, I'll just take some kind of a weighted average of their rating of that movie, and I'm going to use that to impute what my rating would be. Okay, so that's user-based collaborative filtering. So step number one is to come up with a similarity measure between myself and everybody else, find the people that are close to me, use their ratings to try to guess at what mine would be. Just diving in a little bit deeper with user-based collaborative filtering, I start out and I have to create this similarity matrix of users. So it's going to be a pretty large similarity matrix. I really only need half of it, right, upper or lower diagonal. But it's going to be the measures of similarity between every pair of possible users, every pair of users in the data set. There's a couple of measures we can use to get the similarity between any two people. One is something called a cosine similarity, and the other one is just simply correlation. I'm going to talk a little bit about more correlation because I suspect most of us are more familiar with that. Correlation has certain limitations, as you probably all know. It's a linear measure of relationship. There can be other relationships that exist that correlation misses. But I'm going to talk about correlation. The cosine similarity is very popular, especially in text analytics. And anecdotally, at least, I found that it works pretty well. But I'm going to just talk about correlation. Once I find that gigantic correlation matrix, I'm going to impute my ratings of things that I haven't seen. If these are movies, I'm the active user, I'm going to impute my rating by taking a weighted average of the people that are close to me, the people in my neighborhood. And I've got an equation. I'm going to put some numbers in this, a real simple numeric example to illustrate exactly what I'm talking about. But basically, this is what I'm doing. So R hat is the estimated rating or the predicted rating of the active user. That's what the sub A means for item J, or for movie J. That's equal to the sum of these similarity measures. So these would be correlations in my case, between myself and user I, multiplied by the rating that user I gave to item J. Add all those up, and then I divide by the weights, whatever those similarity measures were. Okay? And that's going to give the prediction of what I would rate this movie to be that I haven't seen, based on these other fellows that I have seen, and that are close to me. To put some numbers in it, hopefully make it a little bit more clear, looks something like this. So we start out with a correlation matrix. And this is a correlation matrix I created in R. It's actually pretty easy to do. It's really a heat map with the correlation numbers superimposed on top of it. If I'm the active user, I'm U sub A, user active, I can go across this bottom row and I can identify the people that are closest to me. Just for the sake of example, I've only got 6 other people besides myself. I'm going to assume that my neighborhood consists of 3 other people. All right, so the 3 closest people are the only ones I'm going to worry about. I go across this row. These are my measures of similarity with all the other 6 individuals. And I see that, I can tell this by color or by looking at the number, the numeric value. Users 1, 3, and 4 seem to be the closest 3 people to me. So I'm going to say, okay, those are the folks that are most like me. They see things a similar way that I do. So I'm going to use their ratings, the weighted average of their ratings, to impute my rating. Okay? So I know that those are the guys. Next, I go to a ratings matrix, and it's pretty small and simple because I only have 6 people, and I'm going to pretend here that I only have 8 items, 8 movies. I have actually rated movie 3, 4, 6, and 8, so I don't have to worry about that. I know what I rated those. But what I do want to know, what I don't know from this is how would I have rated movie 1, movie 2, movie 5, and movie 7. Okay? Notice I've got some horizontal blue bars going across this ratings matrix. Those highlight the 3 users that are closest to me. So no number in here matters to me. There's no number in this matrix that matters to me unless it's highlighted by the blue bars. If I want to get my rating, my estimated rating for movie 1, that's R hat sub A1. How would I do that? Well, I take a look at this column and I just look at users 1, 3, and 4. User 1 didn't rate it, so I can't use their information. Users 3 and 4 did rate it, so I'm going to take an average of users 3 and 4, their ratings, but I'm going to weight them by their similarity to me. So I'm going to take the 0.41 times the 3, that's for user 3, the 0.2 times the 4, that's for user 4, add those up, and then I'm going to divide by the sum of these 2 weights. In other words, I'm going to do this. Okay? And I wind up with 3.3 as my approximated rating, and I can do the similar calculations for 2, 5, and 7, and I've got my predicted scores, and from that I can base some recommendations. Okay? I think it's pretty straightforward. The idea, conceptually, it's at least conceptually not too difficult to do. There are a couple of things that I just want to mention about it before I move on. First, I'm looking at raw scores here. I might want to adjust those scores, do some sort of normalization. All right? When I think of normalization, I think of subtracting off the median divided by the standard deviation. I could do that. I could get a z-score, or I could just center by row. So if I look across the rows, I'll get the average and then take every one of those numbers and subtract off the average. Right? Why would I want to do that? All right? Well, if you've got someone like myself who I take a real positive view of these movies, right? Like, oh man, if it's even halfway good or not bad, I might give it a 4, and if it's a little better than that, I give it a 5 out of a 5-star rating. And so I'm always up there on the upper end of the scale. Whereas Dr. Flugheft is much more discerning, and he says, there's no movie that's perfect, nothing could possibly get a 5. So, I mean, even if it's great, if it's super good, I might give it a 4. If there's any kind of flaw, it goes down to 3, 2, or 1. Right? So he's using one end of the scale, I'm using the other end of the scale, even though we're sort of looking at the movies in a similar way. In survey research, we call that scale use heterogeneity. Just means you're using the scale differently. And so I can try to adjust for that by subtracting out the mean. So I'll take those people that rate things really high, like myself, and I'll bring their scores down, hopefully they'll be in line with everybody else. Okay? That's one thing. The other thing is this. This approach can be very expensive computationally, right? Especially if you're working with big data, right? If you're working with big data, if I've got hundreds of thousands of individuals, that's a really big similarity matrix to hold in memory or to use to compute similarity scores. And every time another user joins my group, all right, this matrix gets bigger, right? It's a little bit bigger. That might be one reason, especially for large data sets, that maybe I want to look at the item-based collaborative filtering instead of user-based, because the item-based, the dimensionality of the item-based similarity matrix is just going to be, the number of items. And that's probably not going to grow as fast or get as big as the number of users in a big data set. So that's just something else to sort of keep in mind. So let's take a look at the actual program. I told you I was going to talk about R programming and take a look at the package that I used to create the Recommender Lab in R. It's going to be a user-based collaborative filtering. So I used a package called Recommender Lab. Recommender Lab is more of a template, so to speak, or an infrastructure for developing and testing recommender systems than it is a program to do or create a specific kind of recommender system, a recommender engine, right? So there's a variety of recommender engines that are incorporated in Recommender Lab. You can use them if you want, right? So there's pre-built item-based collaborative filtering, user-based collaborative filtering. So I can just use those things, and there's a few other ones as well. I can allow incorporation of my own algorithm. So if I think I've got a better way of doing things than what's out there, I can write it myself. This is one of the cool things about R. You can do that sort of thing. It allows for sort of a general way, and a consistent way of addressing my data object. And it also does testing. It also makes it very easy to test my recommender system by doing some out-of-sample prediction. I'm going to talk about that a little bit as well. It can handle ratings data and 0-1 data. 0-1 data might be something like market basket analysis, right? So you're looking at who bought what together, and then when you see somebody that bought something that's oftentimes bought with something else, you can say, hey, that's sort of my cartoon at the very beginning. You bought some bananas. People that buy bananas often buy cereal, right? Because they like to put the bananas on cereal or something like that. Okay? So it's kind of a neat package. It doesn't handle content-based recommender systems, right? I'll talk a little bit about another way of doing that if I've got time. But Recommender Lab doesn't do that. It focuses on collaborative filtering. I'm going to take a look at a data set. This is the movielens.org data. This is actually a pretty massive data set. It's really, really big. I'm going to look at a small version, and I've got a reference to this data set at the end. If you want to get a hold of it, play around with it, you can download it off the web. It's free. I actually have about 610 users that have ratings across almost 10,000 movies and about a little over 100,000 ratings in total. And it gives the dates here for when this data was collected. So this is about R, so I got to show you guys some R code. I'm not going to go through this line by line, but I'll talk about it in general. If you've got any questions or if you want to talk about it later, I'll definitely be happy to talk to you. I'm going to load in my data set. There's here, ratings data. And notice I called this long ratings. It's kind of a long file. It's going to have 3 columns. That's what Recommender Lab expects. The first column is your user ID. The second column is your item ID, in this case a movie ID. And it's kind of cryptic, right? Movie 6732 and movie 8194, something like that. That's in your second column. And then in the third column, it's got the rating, right? So if user 1 rated 50 movies, there will be 50 lines for user 1. And if user 2 rated 100 movies, there will be 100 lines for user 2, and so on. So it's a very long data set. I'm going to read that in. I get rid of a variable here that I don't need. I pasted an eagle user ID, so it didn't look like just a number. I get easier to recognize. And then I use this command as long ratings, real ratings matrix to format, to change the class of this object from a CSV file to an object that's recognized by Recommender Lab. Now, if you're an old school R programmer like I am, this seems a little weird. Usually when we change the class of something, we say as.class, right? So as.realRatingsMatrix, matrix, and then an object. In Recommender Lab, they do it a little bit differently, and we'll see this in a couple of other examples as well. But it's really no big deal once you get used to it. I did a little bit of cleaning with the data. It was kind of interesting. I looked at the data, and I saw a couple people that claimed to have watched and rated literally thousands of movies. And I thought, really? You really rated 3,500 movies? Are you kidding me? In this period of time, I may have watched 15 movies, 10 movies in all those years. I'm not much of a movie watcher, but a few thousand, that just seems crazy. So I said, hey, you know what? The row counts, and that's the count of the number of movies watched by an individual. I said, that's got to be something less than 1,000, all right? And the columns, so the rows are going to be now my individuals. So when I do this transformation, I now get a wide matrix instead of a long data set. So I restricted the number of ratings for any single user to be something less than 1,000. And I said, I also restricted the column counts. So this is the counts of times any individual movie was rated. I said it's got to be at least 10. Right? If a movie was only rated once or twice, I don't want that to be in my analysis and be used to try to approximate other ratings because not very many people watch it. Okay? Read it and did that. I did that all over again, right from the beginning, except I made one change here. I read in a file called movies.csv, which are movie names, and I did this SQL left join. I'll talk about that more. And all I really wanted to do here was I wanted to have another object, a real rating matrix object, that instead of having in the middle column this cryptic ID for the movie, it actually had the movie name. Right? So if I wanted to come up with a recommendation for user 512, it didn't say, well, we recommend movies 5376, 4291, and 6321. Right? Rather, it said, we recommend, Big Chill, 101 Dalmatians, and Babe, or something like that. Right? So that's why I did that. In any case, I did the same filtering. Both data sets are going to now be 598 users. So I didn't really lose that many users, just the ones that had an incredible amount, that claimed to have an incredible amount of movies reviewed. And I'm down now to a little over 2,000. So I reduced the number of movies quite a bit. There were a lot of movies in there that were only rated once or twice, and so I got rid of those guys as well. Hey, but I still got a decent sample. The Recommender Lab package, again, it's a framework for developing and testing these recommender systems. It's not going to have all the bells and whistles necessarily that you might want when you're developing a recommender engine. For example, right, any statistician, whether it's a first-year intern on the job or somebody who's won a Nobel Prize and has been working in the industry for years, will tell you the same thing. You get a new data set, visualize it. Right? Look at the data, visualize the data, draw some graphs, draw a lot of graphs. Right? Look at interactions, look at histograms, look at scatter plots, all these sorts of things. Unfortunately, my experience is that a lot of people don't do that and get in trouble pretty quickly when you don't. This visualization is something that's not built into Recommender Lab, but it's easy enough to create if you're using R. But you can do it yourself, which is what I did here. I've got a bunch of code. I'm not going to go through this line by line. Nice about this, but I could have turned this very easily into a function in R and just call it in when I use Recommender Lab. And then all I really have to do is feed in my real ratings matrix objects, and it would immediately create the graphics that I'm going to show you in a second. So what did I do? I did some summaries by column. So these are going to be summaries of the items, which in this case are the movies. I did some summaries by rows. Where's that? Summaries by rows, okay, that's right up here. My row means, okay, that's the summary by individuals, by respondents, and then I pulled out the ratings to put in a data frame so it's a little easier to access. I created 5 different plots. One plot was just a plot of frequencies of the ratings. So what was the rating most often given across all the movies? I took a look at the average rating by user. I took a look at the average rating by item, the number of ratings by user to get a histogram of that, and the number of ratings by item, to get a histogram of that. I put these all together and arranged them in a single template using this thing called grid arrange. Again, if you're old school R users, you're probably familiar with a function called mfrow, where you can say mfrow and then you put in a few numbers and it will arrange sort of a matrix arrangement of multiple plots. You can't do that with ggplot objects, fill that out, but you can do it with this grid arrange, or the grid package. In any case, I said, these are the order of my visualizations, my grabs, my graphic objects, P1, P2, 3, 4, and 5, and I specified the width, the number of columns, and that sort of thing. Okay? And then there There's another grid package that I had to load in just to get the title on top of all of these graphics that I wrote. So in any case, I did all that, and here's what I got. Spit out all this information. On the top, I just got the frequencies for the ratings. So it seems like most often people rated movies a 4. Right? That was typically the rating, which kind of makes sense, right? I mean, you don't really watch a movie unless you think you're going to like it, right? Probably, so you probably do like something about it. It's not all that often that you get a fantastic movie, so 4 seems pretty reasonable. I've got the average ratings by user, all right? So what was the average for across the users? So if I look at each user, took their average and plotted the histogram, got the frequencies like that. Same sort of thing, average ratings, but now it's by item. So for the movies, what were the averages roughly? Okay, something like that. And then I've got some counts here. Down here, I've got the number of ratings, the count of the number of ratings by individual user. Right? So again, this goes up to 600. You can see, maybe you can't see, there's a couple tiny little dashes here. I cut this off at 1,000, right? So they can't have more than 1,000. So it stops there. But it does seem like the bulk of them are right between what? This is 100 and this is 50. This is maybe between, I don't know, 15 and 20, something like that. Most people rated about that many movies. And over here, I got the number of ratings for an individual item. So how many times was an individual movie rated? The max number is going to be what? It would be 598. That would be if everybody in the sample rated that movie, which clearly isn't going to happen. The max number, I've got a little blip here for one of those movies, a little over 300. But again, most of them are down here, somewhere between 50, 25, maybe between 0 and 25, 0 and 30, or not 0, 10 and 30, right? I cut that off at 10, so I have to rate at least 10 times. Okay, so I don't see anything in these graphs that would make me go, wow, something's messed up with the data, but that's exactly why I produce these graphs, right? I can take a look at it and go, well, if I had a spike out here or something like that, I might say, hey, what's going on? Why is that there? Maybe there's an error in the data, maybe something weird is going on that I didn't take into account. I'll check it out. Okay. I can explore the real ratings matrix object with a couple of commands. So I'm going to use that as command again. I'm going to take my real ratings matrix, change its class to a data frame. And again, you might be used to saying as.data.frame and then an object. Here, instead, with this real ratings matrix object, I say as and then the object and then the class. And once it's a data frame, I can apply my usual commands to data frames. One of them is the head command. This is a little mixed command, I think. Here's the first 6 lines. So this tells me the first 6 movies that user 1 rated and what the ratings were. And again, I'm going to use the ratings matrix with names, so I can actually see names rather than numbers. I can take the row means across one particular row. Here I'm just using the ratings matrix because I'm not worried about the names. So for user 1, the first row in this matrix, I get an average of about 4.387. So user 1, however many movies that person rated, I can figure that out pretty easily. But however many they were, on average, he rated them about 4.38756. Okay? So that's looking at information in that object pertaining to users. I can also do the same thing looking at the columns, being column focused, and get information across the different items. And again, the items here are movies. So I can take column means and apply that directly to my real ratings matrix object. And do a head command on that. That's going to give me a list. Do a head command on that. And I get the first few movies in the data set. The Burbs, 500 Days of Summer, 10 Cloverfield Lane, etc. I've seen none of these movies, but I take that back. I've seen this one, but I think it was about 6 years old, so I suspect this is not the same version I saw. In any case, those are the movies and the ratings on them. So the very first 6 movies in my data set and their average ratings. Let's build a recommender system, right? That's what this thing is all about. What do? In order to build a recommender system, I use the recommender command, this keyword right here, apply it to my real ratings matrix object. Have to specify the method. I'm going to specify the method as uecf, so that's user-based collaborative filtering. And I'm going to put in my parameter list normalized by center. So this is just going to subtract off the mean from every respondent before the analysis. I call this object recommender UBCFN, where UBCFN stands for user-based collaborative filtering normalized. Okay, and I can take a look at, if I just type in the name of the object, it gives me some information about how it was created. I can look at the names of the elements that are stored inside of this object, and I can see what those are as well. I can generate some recommendations. First one I want to generate is a top n, what they call a top n list, where I specify n. My n here is going to be 3. So I want to specify for a couple of users here, 451 and 452, which because of the ordering, that turns out to be users 511 and 512, the top 3 recommendations for those 2 folks. Technical detail here, you notice that this is actually a matrix, and I'm only specifying 1 dimension. Usually in R you'll get an error for that, and I need a comma here. With the real recommender, with the real ratings matrix object, I can just put something in those brackets and it knows I'm talking about row. So I'll go ahead and do that for those 2 users. Again, I have to change the class of the object, in this case to a list, and it'll print out what's in there. It'll be the top 3 recommendations from the 2 users. User 1, the recommendations would be Braveheart, Jurassic Park, and Babe. User 2, the recommendations would be Fargo, Star Wars, and Leaving Las Vegas. Another 3 things I don't think I've ever seen. Not much of it. So those are the top recommended ones. I can also just get a matrix of the predictions, the predicted ratings, right? So these may or may not be recommended, but I can take a look at them. Again, I'm going to use, or this time I'm going to use the predict command with just the type equal to ratings, okay, instead of n equals to something. I do it for, actually I'm doing it for 5 users, and I'm just going to look, this is going to do it for 5 users across all the movies. I just want to print out now in the matrix the columns 202 to 204. Just print out 3, just for the sake of screen real estate. I can't fit anything else in there. It's too wide. So I've got the predicted ratings for users 1, 10, 100, 101, 102, so it does this reordering when I turn it into a real ratings matrix object. Notice that one of them has an NA in there. This NA just means that this user really did rate bed knobs and glue sticks. All right. All the other ones are predictions. All right, that's all. Okay. Lastly, what I want to talk about, okay, with this is comparing a couple of different recommender engines based on out-of-sample predictive accuracy. So I want to compare item-based collaborative filtering to user-based collaborative filtering. To do that, to come up with a measure of out-of-sample performance, any of you folks in here that have done predictive modeling know that the gold standard is, you create the model using one set of data and you test it on another set of data. You don't test your model on data that you used to create it. So I have to split this data. I'm going to use this evaluation scheme to set up these data sets or to structure the data sets within my real ratings matrix object. I'm going to use a method equal to split, so I'm going to say split. My training data is going to have 70% of my data. So this is all standard stuff, just the way we would do in any case when we were trying to predict out of sample data. But there is one thing that's a little bit different, a little bit of a twist. I've got this parameter here that says given equals 7. So what does that mean exactly? Why am I saying given equals 7? Well, when I take my trained model that was trained on my training data and try to predict my test data, I have to know something about those folks, right? I can't say that, Tom in my test data set is most similar to other folks unless I know some of his ratings. I have to know a few of them. So I'm going to say, all right, Tom maybe rated, let's pretend he rated 20 movies. 7 of them, my engine, my recommender engine, I can pretend knows that. All right? So I say, okay, you don't have to say you don't know any of those 20. You can say you know 7 of them. And then when you do the prediction will be on the remaining 13. Okay? So it's just a little bit of a twist, right? Just to get the thing started. I'm going to create the recommender engine, both using the item-based collaborative filtering and user-based collaborative filtering. So I've got 2 of these recommender engines. I'm going to run out of time here. Then I'm going to do my prediction. So I'm going to predict using the known data, feed that into my recommender engine and predict the unknown ratings. And then I'm going to use something called calculated predictive accuracy. I'm going to get two vectors of errors. This is numeric data, so I've got a number of different summary statistics, fit statistics. I'm going to just combine them together so they're easier to print out. For the item-based collaborative filtering, I got, and for the user-based, I got RMSE, MSE, and MAE. It does seem that the user-based collaborative filtering does a little bit better, all right? But again, keep in mind that its computation is a little bit more expensive. Okay? So there was one other thing I wanted to talk about, and I got very ambitious, and I got about 10 more slides, and I know I can't do it. We can't talk that fast. But I just want to mention it. There is a module in Microsoft Azure. Microsoft Azure, if you're not familiar, it's very similar to Amazon Web Services. It's software as a service, platform as a service. It's got a lot of different functionality. It does, in fact, have something, a module in it, or a package in it, if you will, called Azure Machine Learning Studio. It's really, really easy to use. It's pretty cool. And probably the coolest thing about it is that it's very easy to deploy a predictive model on the internet. So if you want to deploy a model in your website, or if you want to have a Shiny app and then upload that, you can do it actually pretty easily. So Microsoft, and you can actually get a free account. If you just want to play with it, you get a totally free account and mess around with it. That's what I use. In Microsoft Azure Machine Learning Studio, there is a module called Matchbox. Matchbox, yeah, there it is. MUN 2015 talks a lot about this package. Matchbox can actually be used to do a number of things. It's scalable, so it should handle big data very well. It does handle big data very well. It's kind of a hybrid approach. You can actually put in characteristics of the items. So if you did want to build a content-based recommender, you can actually do it with Matchbox. And you can actually put in other information as well. The ratings, of course, characteristics of the users. All right, so if you want to have some demographics about your users, Matchbox can handle all of that stuff. One of the downsides of Microsoft Azure is that it does a number of things very, very well, at least the Machine Learning Studio. There's a lot of things that it really doesn't do. It just doesn't do it. One of them is data visualization. All right. So if you wanted to run this in Microsoft Azure, what would you do if you wanted to visualize this data on some nice special graphs? Microsoft Azure Machine Learning Studio does provide a couple of modules that take care of that. It's execute R script and execute Python script. So if you can do it in R, you can write it in Azure and you can execute these things there as well. Okay? And again, once it's set up and running, a couple of mouse clicks and you deploy it, you get an API code and a URL, and you can plug that into your website if you want to program websites, which I don't, or you can use it in a Shiny app. That's one. Okay? That's it. All right. Thank you very much. Questions?
We can take questions.
Sure. Okay. Questions? I have put this. Okay, go ahead. Sorry.
So would it adjust your model from if there were a few people who only rated highly rated movies, so the rating would get something higher? Is that if they then move on, or does that affect the ratings at all?
I mean, if they've only rated.
With highly rated movies, and so naturally their ratings are high. It's not that they're being generous; it's that they're only seeing the highly rated movies.
Well, I mean, that should aggregate out if you've got enough respondents, all right? I mean, I've seen highly rated movies that I haven't given high ratings to, right? So, there should be some of that heterogeneity in there. They should probably adjust out. I did copy this deck onto the computer here, and Dr. Fugate will have access to it if anybody wants that code. Visualizations are certainly welcome to it. And I've got more stuff about Microsoft Azure here too. Okay? Any other questions?
about R versus Python?
Wow, a religious question. I'm much more familiar with R. I've never seen anything in Python that I couldn't do in R. I've never seen anything in R that I couldn't do in Python with enough work. Python is a little bit more general. R is more a statistician's program. It's more statistically focused. And I think there probably are some things in R, statistical models, that you might have to work a little bit harder to get to run Python. If you wanted to create a website, you could do something like that with R using Shiny and that, but probably much easier in Python. But I'm an R user. I do like Python. I mess around with it a little bit. I want to learn more about it. But
The code you presented, it's prepared to receive your data and keep the analysis going? I mean, the prediction is kind of changing.
right. You would need some kind of an interface. Good question. You need some kind of an interface to accept the data, put it into an acceptable format, and then feed it to the predict function in Recommender Lab. In Azure, if you deploy this, you can actually get an interface that depends on how you want to set it up. When you test it, you can actually see an interface with empty boxes where you put in the numbers or your ratings or whatever it is, and it'll automatically be fed back to your engine. Come up with a prediction. So maybe a little bit easier using Azure.
Has this prediction model been used to make bots that could also be seen in the human? So you could, let's say you have a human that has certain ratings and certain movies. If you're predicting that they would like 3 more movies, couldn't you just say that they do like those movies, and you could kind of keep predicting at top of your prediction?
Maybe I'm not exactly sure what you're asking. I mean, you want to make a prediction of something that, I mean, you wouldn't want to just pretend that they like it, right? You want to make a prediction in such a way that when they go and see the movie, they say, hey, yeah, this could work. Otherwise, if you say, hey, you really don't like this, and they go out there and see the movie, they go, I don't like this. That big question about validity of your model, I guess. You guys know that Netflix had this huge competition on cable for developing a predictive algorithm, and did you guys know that the people that won this, it was an ensemble of models. It was very complex. They won it, they got the money, and that model was never used because it was too slow to run. So Netflix couldn't use it, but these guys still got upwards of $1 million. Anyways, fun fact.